In this lecture, we will discuss the phase diagrams of some pure substances. We begin with defining some relevant terminologies, and then we will discuss how to determine the degree of freedom of a given system, and finally, how to understand phase diagrams. At the end of this lecture, you should be able to determine the degrees of freedom of different systems and understand and interpret the phase diagrams of pure substances. Let's begin by defining some important terms. First is the state of a system. The state of a system is defined by a set of conditions wherein that system is in equilibrium. These conditions or properties of a system could either be dependent on the amount of the substance, called extensive properties, or independent of total amount, called intensive properties. A system could be fully described by defining one extensive property and several intensive properties. Parameters that are often used to describe the state of a system are volume, temperature, pressure, and mole fraction, which are also known as the state variables. Next, let's talk about phase. It is a homogeneous, physically distinct, and easily separable portion of the system. It may be composed of one or more substances. You know the common phases of matter, the solid, liquid, and gas phases. It is also worth noting that there are several phases of solid for some substances, such as the black and white allotropes of phosphorus. We will discuss the different phases of solids more when we get to the phase diagrams. The number of phases existing in a system, which is denoted by P, may be recognized by considering the number of physical boundaries existing in the system. This physical boundary comprises the interface between two phases. For example, gases, whether pure or a mixture, always form only one phase. A solid that is subdivided into smaller fragments, such as a mass of ice crystals, is also a single phase. A mixture of miscible liquids also forms a single phase, but a mixture of immiscible liquids exhibits more than one phase. A slurry of ice and water has two phases, while a system of solid calcium carbonate decomposing to solid calcium oxide and carbon dioxide in equilibrium has three phases, two different solid phases and one gas phase. The components of a system in equilibrium are the substances present in the system. The number of components, denoted by C, is the minimum number of chemically distinct substances necessary to specify the composition of each phase. For example, a system consisting of ice crystals and liquid water only has one component, which is water, but it has two phases. A homogeneous mixture of sugar and water will form only one phase but consists of two components. Then, we have what we call the degree of freedom or variance of a system denoted by F. This is the lowest number of intensive variables needed to specify the state of a system, or it is the number of intensive variables that can be varied without changing the number of phases that are in equilibrium. When the system has 0 degree of freedom, it is called invariant. When F is equal to 1, it is univariant. And when F is equal to 2, it is called bivariant. Now, how do we determine the degree of freedom of a certain system in equilibrium? We use the concept called the phase rule. Phase rule is used for systems in equilibrium. But how do we know if a system is in equilibrium? It should satisfy three criteria: thermal, mechanical, and thermodynamic equilibrium. Thermal equilibrium means that the temperature is the same throughout and in all the phases of the system. Mechanical equilibrium is achieved when the pressure is uniform at any point of the system. And finally, thermodynamic equilibrium means that the chemical potential of each component is the same in all the phases in the system. Now, before we proceed, let us talk about chemical potential. This is the measure of the potential that a substance has for undergoing change. It will be discussed more in the next lectures, but for now, let us define that it is related to the concentration expressed in mole fraction of the component in each phase. So with those criteria in mind, we know that equilibrium depends on several intensive variables, namely temperature, pressure, and mole fractions. Next, let us derive the phase rule equation. As mentioned in the previous slide, equilibrium, and thus the phase rule, will depend on several intensive variables. Pressure and temperature account for two intensive variables already. Next, we need to determine how many mole fractions do we need to define to effectively determine the state of a system. In total, the number of mole fractions depends on the number of phases and components present in the system. Each phase is described by stating the mole fractions of all components present in that phase. However, take note that the sum of mole fractions is always equal to 1. Therefore, you only need C minus 1 mole fractions to describe each phase, since 1 mole fraction can always be determined by difference. So the total number of mole fractions is just equal to C minus 1 multiplied by the number of phases P. Remember, we are determining the mole fractions because it is related to chemical potential. However, based on the thermodynamic equilibrium, the chemical potential of a component is just equal throughout the phases present in the system. Therefore, you only need to define one chemical potential for each component of the system, since its chemical potential will just be the same for the other phases. So if a component has p number of phases, then the mole fractions in p minus 1 phases is no longer needed because again, you only need to determine one chemical potential for each component. For C number of components, C times p minus 1 concentrations need not be defined. Combining all the intensive variables pressure, temperature, and mole fractions and subtracting the mole fractions that we no longer need, we arrive at an equation for degree of freedom F is equal to 2 for pressure and temperature plus P times C minus 1 for the total number of mole fractions minus C times P minus 1 for the number of mole fractions we don't need to specify. Simplifying, we get the phase rule equation F is equal to C minus P plus 2. We can now use this equation to determine the degrees of freedom for different systems. Next, we move on to phase diagrams of pure substances. Phase diagrams are graphical representations of the conditions under which the different phases in a system are stable. It is composed of areas, lines, and points that correspond to the phases that exist in equilibrium under specific conditions. Areas in the phase diagram, which are separated by lines, represent the conditions wherein a single phase is stable. Lines show system wherein two phases are in equilibrium, while the points where the lines intersect represent multi-phase systems. To further explain this, let us look at some of the common phase diagrams for pure substances. First, let's discuss the phase diagram of water below 374 degrees Celsius and 218 atmosphere. There are three main areas in this diagram representing the solid, liquid, and gas phase of water. In these areas, the degree of freedom is 2, which means that two variables are required to properly identify the state of the system. These areas are separated by three main curves: the melting point pressure curve, where solid and liquid phases are in equilibrium, the vapor pressure temperature curve for liquid-gas equilibrium, and the sublimation temperature curve for solid-gas equilibrium. For these two-phase equilibrium systems, the phase rule predicts 1 degree of freedom, denoting that only one variable is needed to define a system. For example, if pressure is specified, there can only be one temperature wherein the solid-liquid phases can exist in equilibrium. Point A, where the three lines intersect, corresponds to a system wherein the solid, liquid, and vapor phases of water are in equilibrium with each other. This is called the triple point. This is an invariant system or with 0 degree of freedom because this can only occur under set conditions, specifically 0.01 degrees Celsius and 0.006 atmosphere. This point also marks the lowest pressure and temperature that liquid water can exist. The extended phase diagram of water shows that it has multiple solid phases at very high pressures and melts at high temperatures. These polymorphs of water exist due to the difference in the arrangement of the water molecules when subjected to extreme pressures. You may also observe that there are additional triple points which also occur under specific conditions. Some useful information that can be determined from phase diagrams are the boiling and freezing points of the substance. For water, at a pressure of 1 atmosphere, the normal freezing and boiling temperatures are 0 and 100 degrees Celsius respectively. The phase diagram also shows the critical point of water, identifying the critical temperature and pressure at which this occurs. This point marks the point when the densities of the remaining liquid water and that of the vapor becomes essentially the same, that the boundary between the two phases disappears. Beyond the critical point, a single uniform phase called supercritical fluid exists. Next, let's look at the phase diagram of helium. At very low temperatures, helium behaves unusually because of its low mass and weak interactions. Due to that low mass, atoms vibrate with large motion that the only way to make the solid intact and stable is by applying high pressures. In that regard, the solid and gas phases of helium are never in equilibrium. Helium also has two liquid phases, namely helium-1 and helium-2. Their main difference is that helium-1 behaves like a normal liquid, while helium-2 is a superfluid. A superfluid is a liquid that flows without viscosity. There are two triple points for helium wherein the liquid phases helium-1 and helium-2 are in equilibrium with either its solid phase or vapor phase. Similar to helium, sulfur can also occur in four possible phases: gas, liquid, and two solid phases, namely rhombic and monoclinic sulfur. The rhombic allotrope of solid sulfur is stable at room temperature, while the monoclinic sulfur is favored at high temperatures. Sulfur has three triple points, marked with the numbers 1, 2, and 3, each with a specific set of pressure and temperatures. This ends Module 2A. At this point, I hope you now understand how to interpret phase diagrams of pure substances. In the later modules, we will study how to interpret phase diagrams of binary systems. Thank you for listening and see you in our synchronous discussion.